So here is an outline of my talk. I'll start by introducing the system of walking droplets and then provide a theoretical model to capture the walking dynamics of the droplet. I'll then use this model to show the rich dynamical behaviors that arise for a single wave particle entity in free space. Building on this, I'll add an external tilted potential and show the anomalous transport phenomena that arises in the system. At the end, I'll provide a brief summary of the main results. So in 2005, Yves Couder and colleagues in Paris showed that if a bath of silicon oil is vibrated vertically, then a droplet of the same oil can be made to bounce and walk on the liquid surface. So as you see in that video, each time the droplet bounces, it creates a standing wave around itself that decays in time. The droplet then interacts with these standing waves on subsequent bounces to propel itself horizontally. So what you end up getting is a millimeter-sized self-propelled wave particle entity on the liquid surface. Now, if the bath is vibrated at two frequencies, then what we found is that you can get bigger droplets to walk, and these walk much faster, and hence we call them superwalkers. Now, one thing to note is that for both walkers and superwalkers, that the dynamics are non-Markovian. So what I mean by that is that in the regime where the waves generated by the droplet decay very slowly, the droplet is not influenced by its most recent wave, but its dynamics are also influenced by the waves generated in the distant past. So in this way, you have a memory in this hydrodynamic system. So in the high memory regime, where the droplet remembers a lot of its past waves, these walking droplets have been shown to mimic several behaviors that are typically associated with the quantum world. So, for example, if we put the droplet in a circular cavity whose dimensions are of the order of the wavelength of the waves generated by the droplet, then as you see, the droplet will undergo this apparently chaotic looking trajectory. But if the droplet is tracked for a few hours, and if we plot a histogram of where the droplet has been inside the cavity, then you get this coherent wave-like structure in the probability distribution of the droplet inside the cavity. Another example is that if you confine a droplet with barriers which are below the liquid surface, then the droplet will typically reflect from these barriers. But as you'll see now, sometimes it can unpredictably cross the barriers and you get an analog of quantum tunneling. And then when a droplet encounters an obstacle, it will interact with that obstacle, which will affect the motion of the droplet. So for example, when a droplet is fired at a single slit or a double slit, it can diffract and interfere. So in the double slit case, even though the droplet is going through one of the two slits, the underlying wave is going through both the slits and interfering with itself. And then lastly, we can also get quantization in the droplet's dynamics. So if a droplet is placed in a harmonic potential, then you get these discrete set of orbits for the droplet. And if you plot the mean curvature of the orbits versus its angular momentum, then you can get the quantization in that space. So these were some examples of the many different analogs that these droplets exhibit of both quantum and optical systems. All right, so now there have been many theoretical models developed over the years that capture the droplets dynamics. One of the most widely used model is that of Oza et al., developed in 2013. So this model is based on the fact that since the vertical bouncing motion happens very quickly compared to the horizontal walking motion, one can average over the periodic vertical bouncing motion and only look at the horizontal walking motion. So in this so-called stroboscopic approximation, the vertical dynamics are averaged over and we only get the horizontal dynamics. So to get an intuition for this, in the experiments, if we only take one image of the droplet per bounce, and if we stack those images, then we'll get a video which is shown here. So here you can see that there is no vertical bouncing motion because there's only one image per bounce. So the droplet seems like it's just moving horizontally in 2 dimensions. So this is the stroboscopic approximation. So a one-dimensional realization of the stroboscopic model is presented here in dimensionless form. So this is basically Newton's second law, so F equals ma equation. So the first term here is an inertia term, so mass times acceleration. So you can think of the parameter kappa as an effective dimensionless mass. The second parameter there is a drag term. So when the droplet is in air and also when it contacts the underlying waves, it loses momentum and therefore there's a drag in the system. So we model this drag proportional to the velocity. And then the force on the right-hand side is the wave memory force. So this is the force that the droplet receives from the underlying waves. So this wave force is proportional to the gradient of the wave field beneath the droplet. So this force is some coupling constant beta times the gradient of the wave field. Now, this wave field beneath the droplet, that itself is calculated by integrating over all the individual waves generated by the droplet as it moves, right? So you have this integral coming in here because we are integrating over all the past waves. And this f function here is basically the derivative of a, which is the wave field that the droplet generates. So we get this integral differential equation with two parameters that describes the droplet dynamics in one dimension. Now, typically, a Bessel wave field is used for the waveform for the droplet because this provides a good approximation to the experimentally observed wave field of the droplet. So if we use a Bessel wave field in the model and look at the dynamics we get in the parameter space of kappa and beta, then this is what we find. So for most of the parameter space, we have this yellow solution, which corresponds to a steady walking solution at a constant speed. Now, when kappa is small and beta is large, then we get unsteady behaviors emerging. So for most of the unsteady part, we get this light blue solution, which is an irregularly walking droplet. So here, basically, the droplet will walk in one direction for a while and then switch direction, and then again walk for a while and switch direction. So you get droplet performing this random walk kind of motion in this region. And then you get these small isolated regions where we do see periodic behavior. So for example, here in orange, the droplet is performing back and forth oscillations, but there's a net drift in the motion of the droplet. And then similarly, in the dark blue here, we get back and forth oscillations without any net drift. So the droplet traps itself under its own wave field and it just does back and forth oscillations. Now, the Bessel wave field has two key features. So it has oscillations, and there is a spatial decay as you go away from the central peak. Now, if we only retain the oscillation aspect of the Bessel wave field, then we can use a simplified sinusoidal wave field in the model. And if we use a simplified sinusoidal wave field, then this is what we get. So we retain all the qualitatively different types of dynamics that were observed using the Bessel wave field. So we get the irregular walking, the oscillating walkers, and the self-trapped oscillations. But the extent occupied by these behaviors in the parameter space changes because the form of the wave field has changed. But we do retain the different types of behaviors. Now, the reason for using a sinusoidal wave field is that you can convert the integral differential equation into a system of ordinary differential equations when you have a sinusoidal wave field. And in fact, we find that this maps directly onto the classic Lorentz equation, so the classic Lorentz system. So the x variable in the Lorentz system is the droplet's velocity, the y variable is the wave memory force, and the z variable is also related to wave memory forcing. And then the parameters sigma, r, and b are related to the kappa and beta of the droplet. So you get this nice exact correspondence between the droplets equations and the classic Lorentz dynamical system. Now, before I proceed, let me introduce this concept of absolute negative mobility. So typically, if you have a system which is at equilibrium and you apply a small bias force, then you expect the system to respond in the direction of the bias. So, for example, if you have a piece of wire and you apply a voltage, then you'll get a current in the direction of the applied voltage. Now, for systems that are not at equilibrium, you can get counterintuitive behaviors arising where the system will respond in a direction opposite to the applied bias. So this is called absolute negative mobility, or ANM. So this has been observed in both classical and quantum systems. So I'll give you an example of a classical system. So as you see in the schematic, what we have is we have a Brownian particle diffusing in this channel, which has walls at an angle. So when the particle hits the walls, it can reflect off the walls. So in this system, if we add an external constant bias force in the vertical direction, and then look at the average velocity of the particle in the vertical direction, then this is what we get. So we see that for small positive bias forces, we get a negative drift in the vertical direction. So we get a drift which is in a direction opposite to the applied bias. So this is absolute negative mobility. So to create a similar situation in the wave particle entity, we add a constant bias force to the system. So what this will do is this will add a constant term in the droplets equation of motion, and then we get a constant term coming up in the corresponding Lorentz-like system of equation with the sinusoidal wave field. All right, so if we do that, then this is what we get. So what you are seeing here is basically the applied bias on the x-axis and the average drift of the particle on the y-axis. So the different colored curves are for different values of kappa and beta. So first of all, whenever the average velocity is below the x-axis, so below zero, we have absolute negative mobility because we are seeing an average drift in a direction opposite to the applied bias. So we get absolute negative mobility. We also get some other features as well. So we get what's called differential negative mobility as well. So here the average drift is in the direction of the applied bias, but as the value of the bias increases, the drift actually decreases. So you have a negative gradient in the curves. And then we also get these regions where the average drift seems to be almost independent of the applied bias. So we call these lock-in regions. So when we get absolute negative mobility, how do the trajectories look like? So we get either periodic behavior, as you see here. So the droplet is undergoing back and forth oscillations, but there is a net drift of those oscillations in a direction opposite to the applied bias. So we get this for the green curve and the blue curve when it's below zero. And then, for example, for the purple curve here, we get an irregular trajectory when we have absolute negative mobility. So here the droplet is undergoing irregular motions, but you can see that we get these periodic uh, bursts appearing at times. So you get these bursts where the droplet is traveling periodically in a direction opposite to the applied bias. So although the overall motion is irregular, these periodic bursts will eventually result in an average drift of the droplet in a direction opposite to the applied bias. All right, so in conclusion, I showed that a wave particle entity can exhibit rich dynamical behaviors such as oscillations with a drift, oscillations with no drift, so self-trapped oscillations, and irregular walking. And then when we choose a sinusoidal wave field, then we can map the droplets equation onto the Lorentz-like system of ODEs, and then adding an external tilted potential results in anomalous transport behaviors such as absolute negative mobility, differential negative mobility, and lock-in regions. Thank you for listening.